In this lecture, we are going to introduce a concept called deterministic finite automata. This concept is also variously known as finite automata or finite state machines or just state machines. Now, this is a mathematical concept that is extremely useful in digital electronics, hardware, and in general in computer science. For example, when you are thinking of a robot, you are actually looking at a bundle of lots of different finite automata. Similarly, compilers, like the compilers that you use to compile your C program or Java program, they are also variants of a deterministic finite automata. And whenever you play a game, like this game, for example, such game characters are actually controlled by finite automaton. Or when you look at any program with a graphical user interface, like something that will allow you to draw things like this also relies on finite automaton. Now, in this lecture, we are going to see various aspects of finite automaton, not just these things. We are also going to see its mathematical side, where it is connected closely with algebra and also has an interesting application to combinatorics that is little known, but is a very powerful application. But our exposition necessarily will be pretty elementary, where we shall work with only toy examples, and occasionally some of those toy examples will prove useful as well. So let's look at our first example. Our first example is that of a robot, a very simple robot that I have called Humpty Dumpty. Now, this picture that you see is actually stolen from a book, a famous book, Alice in the Wonderlands. It was originally drawn by Sir John Tenniel. I have just modified it a little bit. Now, this robot, just like any other real-life robot, can do two things. It can sense its outside world through some sensors, and it can react. Now both these things, this input and output, are quite limited compared to what we human beings are capable of. Now, in our case, this simple robot can sense only two things: whether you are smiling at it, if you press this button, that's the effect of smiling at it, or whether you are punching it. So these are the inputs. Now, the outputs, there are two. Either it smiles back at you, or it can scowl at you. Now, let's play with this robot for some time to understand how the inputs control the outputs. Suppose I smile at it, and yes, it just smiles back. Okay, let's smile at it again. Well, it just continues to smile back. Now I punch it, and it scowls. Punch it again, scowl. So you can see, if I smile, then it smiles back. If I punch it, then it scowls. Now let's do the following experiment. So I start again from the initial position. I smile at it. Well, it smiles, fine. Now I punch it 5 times. 1, 2, 3, 4, 5. It continues to scowl. Now I smile again at it. And lo and behold, it just does not bear any grudge. Even though I punched it harshly 5 times, it continues to smile back at me as if nothing has happened. Now, of course, we can consider this as the clue to happiness. You just do not bear grudge against anyone. But for our robot, this is really not a virtue. It is a deficiency. It does not have a memory. It does not have a mind to bear grudge in. So it behaves very mechanically. Now, if we want to mimic human behavior, we must endow the robot with some kind of a mind. Now, before going into that, I will just point out that this little thing is basically just a function, right? here is a set of input, here is the set of outputs, and what you are doing is that you are mapping smile to smile back and punch to scowl. That's it. Now, for such a function to really exist, and of course we want the function to be onto because all the outputs must occur sometime or other, we need the output set to be at most as large as the input set. If you have an output set which is larger than the input set, you cannot have an onto function. What does that mean? This means if you want the robot to have various outputs, in that case the only way you can achieve it is by giving it lots of inputs. Now that is something which we do not like. We want to give it little input and still we want it to react to them in a variety of ways. So let us see how we can achieve that in our next example. Our second example is again another Humpty Dumpty, but this time a more sophisticated version. The first thing that you should notice is that while the set of inputs remains the same thing, but the set of outputs is now much larger. It has got 6 elements, 1, 2, 3, 4, 5 and 6. So either the function will not be surjective, not be onto, that is some of the outputs are impossible, or there is something more subtle going on inside. Let's just play with it. Again, as before, I smile at it and I see it smiles back. Okay, I smile again, it continues to smile. Suppose I punch, oh, now it raises its eyebrow. Okay, punch it again. Now it scowls. Punch it again, it now growls. And punch it again, now it grimaces. Now smile at it now, well, it just continues to scowl, it will not smile anymore. So this one clearly is more sophisticated, and you can see that it has a memory because it could distinguish the first punch from the second. For example, when I punched it for the first time, it was surprised. Then when I punched it for the second time, it scowled, and so on. If I just smile it right from the beginning, it will just smile back. But if I punch it first and then I smile, then it will just scowl. Now, how did we endow this robot with a memory? Simple. We just gave it a box called the mind, in which it currently stores its mental state. Now, our robot is very kind and will not mind if we want to look inside its mind. So I will press this mind toggler and you can see what it is thinking. Initially, its mental state is ordinary. Now when you smile, you see two things change. The mental state becomes happy and it also smiles back. Now if you punch, the mental state becomes surprised and the robot raises its eyebrow. So you understand how the mental state is controlling the thing, exactly as it works for a human being. At every point it has a mental state, and when you give it an input, the mental state itself changes based on its current mental state and the input that you have given. And the output is controlled by the current mental state and the input that you have given. Let's just quickly see it. Initially the mental state was ordinary and you smile. So when it is in ordinary mental state and you smile, then it smiles back. But if I punch it, so its mental state now is furious. If you smile now, then it just scowls. So its output depends on two things, the input as well as the mental state. The mental state itself depends on two things, the current mental state or just the mental state at the last stage and the current input. Essentially the way we human beings work. Now that is an example of a finite automaton. This is the quintessential fact that it's a machine which has got input and output and there is this state. this internal state or the mental state that controls everything. Now that we have seen a complete example of a finite automaton, it's time to take a look at the mathematical definition. Mathematically, a finite automaton is defined using its components. We first have three sets. A, the set of inputs. In our example, it was smiling and punching. Then B, the set of all outputs. In our example, it was normal, smile back, raise eyebrow, scowl, growl, and grimace. Then we have the set of all mental states or just states. S, ordinary, happy, surprised, angry, and furious. Then we have two functions that control the state and the outputs. The first function is the output function. We will call it F. It is from A cross S to B. That is, you take an input, the current input, S, the current state of the mind. Based on that, it generates one of these 6 outputs. Then also the mental state is updated by the function which I have called the next state function, G, A cross S to S. If your current state is here and the current input is here, in that case the next state will be in this codomain. So I have got 5 things, 3 sets and 2 functions. Only one other thing is needed, that is the state, the initial state. And initially we start in the ordinary state of mind. So some designated state called the start state or the initial state. So the mathematical definition of a finite automaton is a 6-tuple, 3 sets, 2 functions and 1 element of this set of states. Now we shall take a look at the finite automaton that was behind our Humpty Dumpty sophisticated version. Well, instead of listing all those sets and all those functions, we prefer to present it as a transition diagram. The diagram that you can see here. Well, in the transition diagram, you see certain ovals. These ovals denote the states: ordinary, happy, angry, furious, and surprised. Now, these are connected with some arrows that encode those functions. Each arrow is labeled with something like, so here is an arrow, then it is labeled with something with a slash, something before the slash and something after the slash. The thing before the slash is the input and the thing after the slash is the output. For instance, if you are in the ordinary state and I smile at it, so the input is S is smile and P is punch. In that case, it will move to this state and the output will be smile. And this arrow from nowhere is pointing at ord, which means ordinary is our initial state. And I have also color coded it as red. So let's start playing the game. Suppose I smile at it, then I move from here to here. And since this arrow is connected with the output smile, you see Humpty smiling. Now if I smile again, in that case, I am just taking this self loop, so Humpty continues to smile. Now if I punch, I am going to take this arrow because it is labeled with the input P and it will raise its eyebrow. I have just abbreviated it to raise, so let's do that. Indeed, it raises its eyebrow and now it is surprised. I punch again, now it scowls and it has become angry. I punch again, now it starts growling and it is furious. Punch again, it grimaces, and if you continue to punch, it will continue to grimace. And if you now smile at it, it will scowl and go to the angry state. Keep on smiling at it, it continues in that particular state. So you understand how we can always depict all those 6 things in an arrow diagram. Just one point, here all the outputs are actually associated with the arrows and not with the state. For instance, in this case, I am at the furious state, But when I enter the furious state, I will growl. I punch, in that case I growl. Though I am furious, I am growling. If I punch again, I am still furious, but now I am grimacing. So the outputs are not connected with the states but with the arrows, because the outputs are determined by not just the state together with the current input. So now that we have seen a complete example of a finite automaton, it is time to look into some real-life applications of the concept.